Oh, I hope you're as excited as I am today because we're doing lesson 6.6, Parallelograms on the coordinate plane, which happens to be your last lesson in this unit before the study guide. Today, you'll be able to prove what shape a figure is based on its coordinates. Okay, let's start off with parallelograms. How do we prove something's a parallelogram? Well, there's three properties that we can use to prove that a shape is a parallelogram. Now, the first thing we could do to prove that something's a parallelogram is show that the opposite sides are parallel, right? We know this property is true. So if we could show that opposite sides are parallel, then we can prove that it's a parallelogram. So what am I going to need to know about this figure, right? What would I have to know about AB and DC to show that they're parallel? The slope, right? If I know the slope of AB is the same as the slope as DC, then I know they're parallel. So what am I going to need? The slope formula today. All right, we're going to be doing some slope formulas today. Now we could also prove that opposite sides are congruent. So if I wanted to show that AB and DC were congruent, what would I need to know? I'd probably have to know the distance from A to B and the distance from D to C. And what would I need to find the distances? Think about it. The distance formula, that's correct. So if I could show that each pair of opposite sides are congruent, AB is congruent to DC and BC is congruent to AD, then we know that this is also a parallelogram. And finally, we could prove that diagonals bisect each other. Now, how would we do that? Well, I'll show you. Let's draw our diagonals here. Here's a diagonal and here's a diagonal, right? And they go through this point. Now, this point is very special because it goes through the middle of both of these lines, right? Well, what we call this point that goes through the middle, right? We would call that the midpoint, right? So if I find out that the midpoint of DB is the same midpoint of AC, then I know they bisect each other, and so I'll probably need the midpoint formula. So using these three properties, opposite sides are parallel, opposite sides are congruent, and diagonals bisect each other, I can prove that a figure is a parallelogram. All right, but I only need to use one of these three methods. We'll go through all three today. All right, let's start with method one, prove opposite sides are parallel. Graph quadrilateral PSFT with the given vertices, determine if the figure is a parallelogram. All right, so we're going to first start with proving opposite sides are parallel. So let's start by graphing this. So we got -5, -1, 1, 2, 3, 4, 5, -5, 1, -2, 2, -1, -3, and our last point is -4, -4. Okay, we got this down. It's always good to have it to label it, your points. So this is P, S, F, and T. And let's connect our points with a line. Please use a protractor to make everything pretty. I'm going to use my personal protractor right here. All right, and all right. All right, that looks like a parallelogram to me. And what we want to do is prove that opposite sides are parallel. To do that, what do I need to know about all of these lines? The slope, right? So if I could show the slope of PS is the same as slope as TF, I know those opposite sides are parallel. So how do I find slope again? That's right, the slope formula. M is equal to y2 minus y1 over x2 minus x1. Now if you feel more comfortable counting, that's totally acceptable. We're just going to do it this way today. Okay? So our slope of PS versus TF. We want to show that the slope of PS is the same as slope of TF. So let's try by first finding the slope of P and S. Okay? Let's go. So it's x1, y1, x2, y2. All right? So let's find the slope of PS first. So y2 is 2, y1 is 1, so y2 minus y1, over x2 minus x1. All right? So I just plugged in my points to the slope formula, and when I do that, I get 1, 2 minus 1 is 1, over -2 minus 5 is 3. So my slope is 1 over 3. Now if you feel more comfortable counting, that's totally fine. So you could say that the slope of this is 1 over 1 up 1 over 3, so the slope is 1/3. Okay, well, for you guys, I want you to know this. I want you guys to use the slope formula when you're finding the slope. But today, so since I don't want to waste your time on anything, I'm just going to be counting slopes. But you need to use the slope formula. So the slope of PS is 1/3. All right, that's our slope of PS. Now, to find the slope of TF, I want you to use the slope formula. I'm just going to count. So it's up 1 over 3. So my slope of TF is 1/3, and that is the slope of TF. So sure enough, I've just showed that PS is parallel to TF. Awesome. All right, the next part is showing that SF, right, our other line over here, SF, is parallel to PT because both sides, both sets of opposite sides need to be parallel, or else it could be a trapezoid, so you have to do it twice. So once again, I'm going to use my counting method. I'm going to repeat this again. I want you guys to use the slope formula. I get to be lazy, and I'm just going to be using PS. I'm just going to be using the counting method. So the slope of PT, let's count it out. It is down 1, 2, 3, 4, 5 over 1. So my slope of PT is -5 over 1. That's the slope of PT. And the slope of SF, it's down 1, 2, 3, 4, 5, and over 1. See right there? So I went down 5 over 1, and that is the slope of SF. And that shows that these two slopes are once again the same, so I know those are parallel. I'm going to repeat again. I want you to use the slope formula. I was just being lazy. So we've just showed that opposite sides are parallel. So the final thing we do is we actually write a proof. And the way you do this is a flow proof right here. And what you do is you state what you did. We showed that the opposite sides were parallel. We state the property we used, and then we state our conclusion. So what that looks like is this. We know that PS is parallel to TF because we proved that. And we also know that PT is parallel to SF because once again they have the same slopes. The property that we're using here to prove it is that opposite sides are parallel. So the conclusion that we reach because opposite sides are parallel, well, it's that this quadrilateral PSFT is a parallelogram. All right, we proved it by using this property. Opposite sides are parallel. Let's try this again, but we're going to use a different property this time. We're going to use opposite sides are congruent, and for that we're going to need the distance formula. Okay? What is the distance formula? So D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Memorize that. It's very helpful. All right? So by finding the distances, we could show that all the opposite sides are congruent, and that's another way to show that a figure is a parallelogram. So graph quadrilateral ROMY with the given vertices, prove the figure is a parallelogram. Well, we got R, which is -2, 5, 1, 2, 3, 4, 5. That's our R. O is 1, 3. That's our O. M is -3, 4. -4. -3, 1, 2, 3, 4. That's M. And Y is -6, -2. 1, 2, 3, 4, 5, 6, 1, 2. And that is our Y. All right, beautiful. Let's connect it up to make our parallelogram. All right, that looks quite beautiful. And now we're going to prove that opposite sides are congruent, so this must be a parallelogram. So let's start with this. We want to prove that RO has the same distance as YM, okay? So the first thing we do is find out what the length of RO is, and we can use the distance formula for that. So the distance formula for RO is, remember, D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Plug everything in. This is x1, y1, x2, y2. We plug everything in, and let's see what we get. X2 is 1 minus negative 2 squared plus y2, which is 3 minus 5 squared. Take the square root of all of that. D is equal to the square root of, let's see, 1 minus negative 2 is 3 squared, plus 3 minus 5 is negative 2 squared. So D is going to be equal to 9 plus 4, so it's the square root of 13. All right? So this is the square root of 13. Awesome. Next part, we're going to prove that we have to prove that ym or my is congruent to this. So we're going to find the length of my with the same distance formula. So x1, y1, x2, y2. All right, and we're going to plug this into the distance formula. So D equals. Now I want you to do this once again on your own, but I'm going to skip through all that because I don't need you watching me doing the distance formula 3 times, and this should give you the square root of 13. All right, if you've done this correctly, and ym is also the square root of 13. You keep going. I want you to find the distance from O to M, and R to Y. All right, you find those distances. When you find those distances, show that they're congruent, and then you write your final proof. So I don't want to go through all of this, but you should be doing this on your own. I'm going to check your notes for this. Find the distance from O to M, and then show the distance from Y to R. Use the distance formula. And when you've done that, you've shown opposite sides are congruent. So how do we write our proof? We show that RO is congruent to MY, which we've done all the work to show. And we show that OM is congruent to YR. All right, the property that we're using to prove that this is a parallelogram is that opposite sides are congruent. And because of that, we have now proven that ROMY is a parallelogram. All right. Okay, for method 3, prove diagonals bisect each other. Okay, to do that, we just have to show that both diagonals have the same exact midpoint. Let's see why. Let's draw it out first. So J is negative 3, 1. All right, that's our J. K is 1, negative 6. 3, 4, 5, 6. L is negative 7, 7, negative 3. 1, 2, 3, 4, 5, 6, 7, negative 3. And our M is 3, 4. So 1, 2, 3, 1, 2, 3, 4. All right, let's connect it up. Let's draw our parallelogram here. J to M, M to L, K to L, and finally J to K. All right, that's a fine looking figure, much like a parallelogram. Looks like a parallelogram to me. But the next part we're going to do is try to show that the midpoint of the two diagonals, which is M and K, and J and L, are exactly the same. So let's look. So M and K, all right, and J and L. Those are our two diagonals, and they seem to have this point of intersection right here, which should be the same. So if they have the same exact midpoint, we know they bisect each other, right? Because that would be congruent to that. And this segment would be congruent to this segment if that's the midpoint, and that means diagonals bisect each other. So let's see if they in fact do have the same midpoint. First, we're going to find the midpoint of JL. Remember, we add the x's, add the y's. So let's add the x's of J and L. The x's are negative 3 plus 7 for JL divided by 2. And we'll add the y's, which is 1 plus negative 3 over 2. When we do that, we find out that M, which is our midpoint, is going to be 4 divided by 2, which is 2, and negative 2 divided by 2, which is negative 1. So 2, negative 1. which looks exactly like what we got here. Now, if the midpoint here is exactly the same, we know the diagonals bisect each other, so let's see if they have the same midpoint. So Km, let's try those points. So we're going to add the x's. K and M, 1 plus 3. All right, I'm just adding the x's of K and M, 1 and 3, and divided by 2. All right, and we're going to add the y's. The y's are -6 and 4. So plus -6 plus 4 divided by 2. Well, let's see. 1 plus 3 is 4, divided by 2 is 2. -6 plus 4 is -2, divided by 2 is -1. And sure enough, I have the same midpoint. So, we just write our proof statement now. We know that the midpoint of Km is 2, -1. We know the midpoint of JL is 2, -1. Because our midpoints are the same, because the midpoints are the same, we know diagonals bisect each other. And since this property is true, we know KLMJ is a parallelogram. Alright, we've just been proving parallelograms, but let's say we want to prove other shapes like a rhombus. What properties can we use? Well, the rhombus we did before. We could show that all sides are congruent, right? That's like the main thing about a rhombus. So if we showed that all sides are congruent, we can show that a figure is a rhombus. So how am I going to show that sides are congruent? Remember the lengths. Well, the way to find the length of something is the distance formula. So what you'll need is the distance formula to show that all sides are the same length. And if all sides are the same length, it is a rhombus. 2, to show that it's a square, we need to show that once again all sides are the same length. But that could just be a rhombus. So how can we make sure that it's a square? We need a second property that only a square has. So all sides are congruent and diagonals are congruent. Right? Now, because a rhombus, that's not true. The diagonals are not congruent, but in a square that is. So we would know that this is not a rhombus, but a square if both all sides are congruent and the diagonals are congruent. And those are all the lengths of things, so we would once again need the distance formula. And finally, if we wanted to show something's a rectangle, well, what are the 2 properties that we can use to show something's a rectangle? Well, we could show that diagonals are congruent. You know what? That would be enough. But it could be a square, so if you wanted to show that it was a rectangle, but not a square, because this shows you that it's a rectangle. That's already proven. But if it's not a square, all sides are not congruent. That would help show that it's not a square, though. But basically, you could just use diagonals are congruent. And once again, you just need the distance formula. Alright guys, hopefully that sets you up. This is your last lesson. Good luck to you, and may the force be with you.